So in this lecture we are going to talk about the very first introduction to conformal mapping. We are already familiar with the type of mapping. Let's say we have some number or a series of numbers in the z plane and we know how to define a map. Let's call that map with f of z, and we know that this is a map that will transfer the inputs of the z plane as the output of the w plane. So this was one sort of mapping, and now what we want to do is that we want to discuss the special type of mapping that is known as conformal mapping. So the motivation behind this, that means one of the motivation would be to solve the Laplace's equation that was given by this. To solve this kind of equation, one can adopt many methods, but it turns out that if this equation is defined in a domain, then the solution would be greatly simplified if we could map the domain into the upper half plane or into a unit disk. And this is where we will use the tools from conformal mapping. So let us first try to look at things in the following way, is that we define a map that is given by w is equals to f of z like this, but we haven't really specified what type of mapping this is. That means whether this f of z is analytic or it's non-analytic and so on, and this is where we will put in some restrictions and we will see that we will get some very interesting outcomes. So the first thing we need to do is that we need to say that, okay, if I have some function f of z and we assume that this function f of z is analytic and non-constant in a domain D of the complex z plane. So this f of z is analytic and non-constant in a domain D of the z plane or the complex z plane, whatever you want to call it. If this is the case, and for any z belongs to this domain, that means any point inside this domain, if f prime of z is not 0, that means we have a non-zero value for our derivative at that point, then this mapping is conformal. Then this mapping, by this mapping we mean that w equals to f of z is conformal, which means that it preserves the angles between two differentiable arcs. So this is something new, that means it's a piece of new information. So let me highlight this thing with a different color. That is, it preserves the angles between two differentiable arcs. So what does this new piece of information tells us? Let's try to draw them. Let's say this is the z plane and this is the w plane, and let's say I have two curves. Let's say one of them like this, and I can have another curve like this, and let's say this is a point where they intersect, and I can draw two tangent lines like this. small tangent lines. And now what we want to do is that we want to map this whole picture over here into the W plane, and let's also denote the angle between these two curves, these two tangent lines is theta on the Z plane. If we map this picture on the Z plane to the W plane, then again we can get two curves like this, and let's say this is now their intersecting point, and if you draw two tangent lines like this, then this theorem tells you that the angle would still be theta. So this is what preservation of angle means. So this is known as the preservation of angles. Now how do we prove it? We prove it using the following way. At first we will try to look at what happens to these tangent lines as they get mapped via this W equals to f of z relation. That's the first thing we want to see, because if we can analyze what happens to the angle or this argument, let's say this is the argument some theta 1, what happens to this theta 1, then by a similar analysis we would be able to find what happens to this theta 2, and from there we can actually see that what will actually happen. And let's call this theta 1 prime in the mapped frame and theta 2 prime like this. Okay, so the first thing we want to see, how do these tangents rotate under this mapping criteria. So what we can do is that we know that if we have a curve on a complex Z plane, we can use some parameter to represent that curve. So a curve on Z plane can be parameterized using some, let's call that parameter S, parameter as z equals to, z of x, it should be z of s, because we are representing the curve in terms of the parameter. So this would mean that x and y, both of them can be written in terms of s. Circle would be a very good example, because if you take theta as a parameter, keeping the radius constant, then you can easily show that this equation would, let's say this equation leads to a circle, then you can easily show that you can represent this in terms of a theta, right, using the polar representations r cos theta for x and r sin theta for y. So that is one of the examples. So if this is true, we are representing a curve with some parameter, then we can imply the chain rule and write it like this. This is not actually a chain rule, but though it doesn't look like one, but indeed it is, because this is like an implicit differentiation, because at the end of the day this x will come in terms of s, y will come in terms of s. So we can write it as I dy of s as this. Why we are doing this, it will be clear in a moment. Now what was our mapping criteria? That was W was written as f of z, right? Now since z itself is coming in terms of s, the parameter, and we are taking some function of z, and z is coming in terms of s, so from there we can say that W will also come in terms of s, like this. A simple example would be to write W as z square, and let's say z is coming in terms of s plus 1, like this, and you just put s plus 1 over here, and you can easily see that W is also coming in terms of s. And after this, what we want to do is that we want to take the derivative at some point. But what is that point? That point would be some s0. That means we are fixing the value of some parameter at a certain point. So if you look at our picture, and if you look at these intersection points, though this is the z plane in terms of x and y's, and let's say this is w plane in terms of u and v, this point x0 y0 would correspond to some s0. Alright, so we take the derivative of w with respect to s in some parameter point denoted as s0. Now we can use the chain rule, and this will be nothing but f prime of z of s0, or you can keep the s there intact, that's your wish, and this would be dz by ds, right? This is also meaning that you are evaluating the derivative at s is equals to s0, and let's call z of s0 as z0. That means this is just x0 plus iy0, or x0 plus ix iy0. So why are we doing all this? Why are we taking derivatives? Because remember, in our definition of the conformal mapping, we are saying that first we are taking some domain, and then we are taking a particular point inside the domain, and we are arguing that the derivative is not zero, and this will enable us in the analysis of the angles, because these tangents are related with the derivative itself. So now, since f prime of z0 is not equals to 0, since f prime, that is the derivative given on that particular point z0, that belongs to the point given by the s0 point of the parameter, and z prime of s0, which is also not 0. Okay, it follows that this guy over here, that means dw by ds at point s is equals to s0, which is written as w prime of s0, this is also not equals to 0, right? So what we can do is that we can write this line, which we label as equation 1. We can rewrite 1 as w prime of s0 is equals to f prime of z0 z prime of s0, right? But you have to be careful about doing these derivatives, because this f prime is telling you that this is a derivative with respect to z, while this z prime is actually telling you this is a derivative with respect to s. Alright, so these are the things you need to be careful about. Now consider this, the argument of this w prime at this point is 0. This should be equals to argument of f prime of z0 plus argument of z prime of s0. Why? Because if you have two complex numbers written as z1 z2 and you take the argument of it, this is just argument of z1 plus argument of z2, and this is easily provable, as you saw in the first week's lecture, that if you just represent them in polar form, the arguments add up. Alright, so what does this tell us? What does this equation tell us? Let's say this is equation 2. You see that this w prime is actually the tangent at the w plane, right? This is what it gives you, because if you recall from real variable calculus, that once you find the derivative at a particular point, you can then use that derivative to find out the angle that a particular line is making with the positive x-axis. This is what is exactly happening over here. So this w prime, that means the argument of this w prime, is actually telling you that the angle that this tangent, let's say one of these tangents, made in this W plane is equals to the angle it made on the positive, angle it made with the positive x-axis in the Z plane over here, plus there is this derivative guy. This is an extra piece. Okay, so that means, let's say we are analyzing for this curve, this tangent, and let's say it made an angle of theta 2 in the Z plane, and in the W plane it made an angle theta 2 prime. So according to this analysis, theta 2 prime would be theta 1 plus the argument of f prime of z naught. That means it's getting rotated by this amount. Alright, and once you consider this, the rest of the analysis that conformal mapping preserves angle is pretty straightforward. Is that this is an analysis for one of the curves. So as you can see, I draw two curves that intersect at some point, and that point is given by z naught in the Z plane. It is represented with the parameter by s naught, right? So you can do a similar analysis for the other curve, and for the other curve, let's say we are writing the other curve as not w equals to, but let's say some g. So similar analysis would yield the result that this g of s naught, since they are intersecting at that point z naught, which is represented with the parameter s naught, so this will be equals to f prime of z naught, and here you will have z prime of s naught, right? And if you want to distinguish that this is actually for the second curve, you can always put as z1 over here. Okay, and now again you can take the arguments of this guy. Argument of this whole thing would be equals to argument of f prime of z naught plus argument of z1 of s naught, and then if you call it equation 3 and you subtract one from the other, so you would have argument of g of s0 minus argument of w prime s0 equals to argument of z1 s0 minus argument of z prime s0, right? So this is the if you write in terms of theta, so theta 2 prime was this, so theta 1 prime, sorry, this should be theta 2, and theta 1 prime would be given by theta 1 plus argument of this, the same quantity, and you can easily see from here that theta 1 prime minus theta 2 prime is equals to theta 1 minus theta 2. That means the angle between them is now conserved. So this is one of the critical properties of these conformal transformations, and it turns out that not only conformal transformation preserves the angle between these differentiable arcs that is written in terms of w prime, that is a very small segment of the tangent, right, or small segment of the curve, whatever you want to call it. It also magnifies the points near that z naught point. What I mean is that if you want to write it as a theorem, it says that if our f of z is analytic, this is analytic, and it is non-constant over some domain D, and for any point z belongs to D where f prime of z is not equals to 0, just like we defined conformal transformation, this transformation W equals to f of z this will magnify distances near another point z0 by the factor of the derivative of the f at z point. That means that if you have a point z0, then under this transformation distances near z0, we are taking a particular point, will magnify by a factor f prime of z0, and there will be a modulus. This will be the factor, and this is pretty easy to prove. Note the fact that since for any point that is the point of interest, the derivative at that point is not 0, we can say that okay, this is not 0, right? So this is something which is not 0. Then how do we write the derivative at that particular point? What we do is that we write this derivative as limit of z goes to z0 f of z minus f of z0 z minus z0, right? And now we want to see the modulus of it. So if you take the modulus on both sides and use the property of the modulus, you will see that this breaks down into z minus z0 modulus and f of z minus f of z0 modulus of this thing, right? So what do you have finally? What you have is, if you take this modulus of z minus z0 on the left hand side, you will have z minus z0 f prime of z0, this limit z goes to z0, and f of z minus f of z0, right? So we are almost done. Now if we picture it in the z plane and the w plane, this z minus z0 is a small differentiable, okay, let us not call it differentiable right now, it's a small segment in the z plane, right? And this f of z and f of z0, these are 2 points in the w plane. So this is a small segment. Why am I calling it a small segment? Because the z0 would go to the z would go to z0, so that's why I'm calling this a small segment. So what this equation is telling you is that the segment on the w plane is equals to some factor, this is the factor, times distance on the z plane between these 2 points. So that's why we are calling it that it gets magnified. Alright, so if this segment looks like this, it will be a bit bigger, or it might shrink down as well. So these are the 2 key properties of a conformal transformation or a conformal mapping. Now I want to end this lecture with a very simple example, is that how we can get used to the basic algebras of this conformal mapping. One example would be, let's say that we are defining some transformation 2z plus 1 by z, something like this, and what we want to show is that it maps the exterior of a unit circle onto the exterior of an ellipse. Ellipse which is given by u by 3 whole square v square equals to 1. So that means that if you have a circle on the z plane and the exterior points, so let me draw the interior with some red, because this is not we are considering. We are considering the points that are exterior to this circle, and this problem tells us that if you define a map like this on the W plane, this will be mapped to exterior of an ellipse. Alright, so let's try to solve it. So we can write z as, so this is the solution, z as x plus iy, and we just put it over here and see what happens. So z is equals to 2x plus iy, then you have 1 upon z, that is 1 by x plus iy, right? But we don't want to keep a complex number in the denominator, so we write it as 2x plus 2iy plus x squared plus y squared, and then you have a x minus iy like this. And if you want to keep the real and the imaginary parts together, you can do that from here, but I won't do it right now. And there is another thing that you can use to simplify your life, is that you see that it's telling you the problem, that is, this is a unit circle and you are considering all the points exterior to that circle. Alright, so at the boundary of the circle you have x squared plus y squared equals to 1. This is the boundary. For the exterior you actually have something like this, x squared y squared greater than 1, because the boundary itself will be an exterior, and for interior you will have something like this, less than 1. So you can use this condition over here and simplify this thing a little bit. So this will give you actually 2x plus 2iy plus x minus iy, and then you do the algebra. This is just telling you this is 3x plus iy, and this is what w in terms of x and y, right? But w itself is a function of complex variables on the w plane, so you can write it as u plus iv. That's what we are interested in, that we want to see what x and y turns out in the uv plane. So u should be written as 3x, and y should be, sorry, not y, it should be v, and v should be written as y, right? So what you have is x equals to u by 3 and y equals to v. Now the exterior region are of the unit circle is given by x squared plus y squared is equal greater than 1, since this is a unit circle. And you can just now paste this the values of x and y into over here, and you will have u by 3 whole square plus v square, which is equal greater than 1. And this is just an equation of an ellipse, right? Because if you take the saturated case where this whole square plus v square equals to 1, this will represent an ellipse, and the greater than symbol will actually mean the points outside the ellipse. So this will be it for today, and in the next lecture we're going to see some conformal mappings where this restriction of the derivative not being 0 will be lifted. Thank you.